Hi guys, it's Daniel here, and I'm going to solve one of my own problems. So let's look at it. Let x sub 1, x sub 2, x sub 3, be the list of positive integers in strictly increasing order such that the quantity x of x plus x factorial divided by the quantity x plus 1 is an integer. Find x sub 100. So at first glance, this seems like a really weird problem because there's an x power of x plus x factorial, and this stuff usually doesn't mix together. So let's see what we can do. First off, we notice that x power of x plus x factorial divided by x plus 1 being an integer, that's basically saying that x power of x plus x factorial is divisible by x plus 1. Which also can be written as x power of x plus x factorial is congruent to 0 mod x plus 1. Now what we can do is take this in cases. X power of x is the first case and x factorial is the second case. And when we consider the mod x plus 1 values of x power of x and x factorial, and find when they match and become 0 mod x plus 1, we know that it's a solution. So let's first look at x power of x. X to the power of x. So first of all, we know that x is congruent to negative 1 mod x plus 1. Therefore, x power of x is congruent to negative 1 to the power of x mod x plus 1. This means that when x is even, then x power of x is congruent to 1 mod x plus 1, and when x is odd, then x power of x is congruent to negative 1 mod x plus 1. So now let's look at the second part, x factorial. To do this part, we need to know a useful theorem in number theory, which is called Wilson's theorem. It states that for any prime p, we have that p minus 1 factorial is congruent to negative 1 mod p. Now, we can also see a corollary that if p minus 1 is not, if p is not a prime, let's say that it's k. Let's use a different color. It's k. K minus 1 factorial is congruent to 0 mod k. This isn't too hard to see because since k is not prime, k can be separated into its factors. And each of these factors is less than or equal to k minus 1. So therefore they must be inside k minus 1. So let's go back to x factorial. So if x plus 1 is prime, then we know that it's congruent to negative 1 mod x plus 1. So let's write that down somewhere. Let's back to red. If x plus 1 is prime, then x factorial is congruent to negative 1 mod x plus 1. Now, if x plus 1 is composite, then x factorial is congruent to 0 mod x plus 1. We can clearly see that if x plus 1 is composite, then since x factorial is congruent to 0 mod x plus 1, to have x to the power of x plus x factorial congruent to 0 mod x plus 1, we must have x to the power of x be congruent to 0 mod x plus 1, but that's not possible. Therefore, we must have x plus 1 be prime. So let's write that down. X plus 1 is prime. When this happens, x factorial is congruent to negative 1 mod x plus 1. So we want x to the power of x, it be congruent to positive, we want x to the power of x be congruent to positive 1 mod x plus 1. Therefore, x is even. X is even. Now there's a special case that we need to consider, but in this part, but I'll leave that for after we solve the general case. So since when x is even and x plus 1 is prime, that basically means that x plus 1 is all the odd prime numbers. For example, x plus 1 equals 3, 5, 7, 11, and so on, while x is equal to 2, 4, 6, 10, and so on. So we're almost done solving the problem. We have a list of possible x such that x to the power of x plus x factorial over x plus 1 is an integer, which is when x equals 2, 4, 6, 10, 12, 16, and so on. And now there's the special case I mentioned before. If x is equal to 1, then we can have x to the power of x also be congruent to negative 1 mod x plus 1, and still have x to the power of x plus x factorial be congruent to 0 because we're doing mod 2. And if you subtract 1 or add 1 from 1 mod 2, you still get 0 mod 2. So we need to check x equals 1 and see if that gives an integer. And sure enough, 1 to the power of 1 plus 1 factorial divided by 1 plus 1 is an integer. It's equal to 1. Therefore, we have the special case x equals 1. So this basically means that we have x equal any prime minus 1, because prime number 2 minus 1 is 1, 3 minus 1 is 2, 5 minus 1 is 4, 7 minus 1 is 6, 11 minus 1 is 10, and so on. Therefore, x, let's write it over here. Therefore, x sub 100 is equal to the 100th prime number. 100th prime. And this, you can check a list or something like that. Well, oops. X power of 100 is equal to the 100th prime minus 1. Minus 1. Can't forget the minus 1 there. So we can check a list and we find that the 100th prime is 541. And we subtract the 1, and so our answer is 540. And we're done.
Hey guys, I'm here back with another math video. Today we're doing a geometry problem created by Daniel Liu. It might not be original because it's sort of generic, but he made this problem. And so without further ado, let's do it. So, look at the problem, pause the video if you need to. Yeah, it seems easy at first, but it's actually not. So, pause the video if you need to, just look at it. Okay, So if you want the solution, first let's take a look at theta right here, and we notice that theta is